Hello, ladies and gentlemen. How are we doing tonight? It's another special edition of CP Physics. What we're going to be talking about today is when you have forces applied at an angle with respect to a surface. This is going to get heavy. You're going to have to try. So, first off, what am I talking about? What I'm talking about is how up until this point, when we've been working these Newton's second law problems, you've got an object, typically it's just sliding along a surface, okay? You have a force applied in one direction, you got friction acting in the other direction. And life is pretty easy because, well, you know you're not going to fall through the floor. You know you're not going to launch up into the air unless it's, a vertical motion problem. But your acceleration is going to be in this x direction, and it's just going to be like if this is 8 and this is 12, your net force is going to be force applied plus force of friction, which force applied was 12 plus a negative 8. Your net force is 4, right? Easy. And then it's going to accelerate according to that net force being 4 in that direction, right? Okay. We've no longer got that because sometimes forces are applied at angles. So you got to be able to actually analyze that stuff. So a couple of brief notes for you. I will post this PowerPoint, but it's pretty quick. What you're going to be getting more out of this is the tutorial and the walkthrough on the problems that I'm going to be doing here. But let's just talk conceptually about this first. So up until this point, we've always had forces. Well, you know that acceleration is always going to occur in the direction of the net force. So the combination of all of the forces. So here in this delightful little example, you're going to have a net force acting to the left because you've got 75 newtons pulling to the left, 35 newtons pulling to the right. So those are unbalanced, whereas the vertical motion are balanced. You got 100 newtons up and 100 newtons down. Okay, so your acceleration is obviously going to be occurring to the left. Now, something to keep in mind, these forces are perpendicular to one another. You've got this y direction set of forces and this x direction set of forces. Now, it doesn't matter what the magnitude of the y direction motion or forces are, what the magnitude of them, they could be 10, 100, 1,000, 100,000. It doesn't matter because the net force is acting in the horizontal direction. So these guys don't have any effect, this normal force and this gravity or the force of the weight. Okay, the only thing that matters is this force applied and that force of friction. Those affect the acceleration. Okay. So when we are dealing with forces that are not parallel or perpendicular to it, when they are applied at an angle, okay, the first thing we need to do is we need to consider that it's not just pulling arbitrarily upwards. It is pulling relative to the surface, okay? The direction of the acceleration is 9 times, 99 times out of 100 going to be parallel to the surface. Very rarely are you going to be launching up off of the surface or falling down through the surface, okay? So the surface is what the angle needs to be taken in respect to, okay? Whether you are pulling upwards on something or pushing downwards on something, okay? That means you break that into x and y components. So like if our applied force is this 80 Newton force applied, it's at this 30-degree angle, that means that you are going to have an x component acting in this direction and a y component acting in this direction. And they will both be affecting their forces that are acting in their planes, okay? This x direction force is not going to affect the force of gravity or the normal force, okay? It's just not going to happen. So that's the basic conceptual intro. Now I'm going to run through a couple of examples and then give you some problems to actually practice with this, okay? So where is it? There it is. So like I said, we are going to be applying a force at an angle now, okay? So just to give you an idea of a simple, quick one. if we are pulling with a force of, let's say, 100 newtons at an angle of 30 degrees. Now, back when we were doing our normal vector motion problems, the first thing I told you to do was to break any vectors that were acting across multiple dimensions, so this x and this y, into x and y components. So what we need to do is we need to do exactly that. So just to give you a wording or a setup for this problem, this is a child pulling a wagon, okay? So mass of the wagon, we'll call that, let's say, 75 kg with the child in it. Our angle is obviously 30. Our force applied is that. And we're going to keep this simple at first and say friction is 0. We have a frictionless surface because we have wheels on our wagon and they work really well. I want to know what the acceleration rate is of the wagon. Okay? So, with our force diagram on this, I'm using colors. I invite you to do the same. We know that there's going to be a force of gravity acting. We know that there is going to be a force normal acting, right? Well, also, we have this force applied in the y direction acting. We also have a force applied in the x direction acting, okay? Now, one of these forces is actually going to cause it to accelerate. I'll give you a hint. If it's on the ground, just draw a little quick picture of our wagon, our child in the wagon, and then somebody pulling the child in the wagon, okay? If it's floating along the ground or if it's rolling along the ground, our acceleration rate is going to be in this direction, okay? It is not going to shoot upwards off the ground. It is not going to fall downwards through the ground, okay? So, therefore, we should look at this x direction to figure out where our acceleration is going to be. In fact, that was our question, acceleration. We know that acceleration is net force divided by mass, right? Well, what's the net force? Which direction is that net force going to be acting in? Well, that's going to be acting in the x direction. We're going to have a force applied in the x direction divided by our mass because those are the only two forces we've got. So we have to break this into our x and y components. So FAX, gosh, SOHCAHTOA never goes away. It's the cosine function because it's the adjacent leg. So we're going to take our force applied times the cosine of theta, and that will give us our force applied in the x direction. So 100 times the cosine of 30. All right. I got 86.6 newtons. All right. Just for fun, let's figure out what's going to happen with our force applied in the y direction. That is the opposite leg. So that means we're going to use sine function. Force applied times the sine of theta. So that's going to be 100 times sine of 30. Make sure you are in degree mode for this. All right, so we've got this happiness going on where we know we're pulling upwards with a force of 50, and we know we're pulling horizontally over with a force of 88.6. Since we are just going to be moving simply horizontally here, the only force that actually affects its motion is going to be that 88.6. Okay, so this problem right now just got boiled down to this problem, this initial problem. Even simpler because we don't even have friction, okay? This person in the wagon is going to behave as though they are this problem here because your net force is acting horizontally, okay? So to complete our problem, we're going to say our net force in the x direction is going to be 86.6 divided by our mass of 75. I'm getting 1.15 meters per second squared. That's going to be our acceleration rate. Okay? So, now, question for you. What happens in the y direction? Okay? So, obviously, in our y direction, are we accelerating off the ground? No. Our acceleration in the y direction is equal to 0 meters per second squared. Okay? So, that means the net force in the y direction has to equal 0 newtons, right? Well, when the wagon was just sitting there, it had a mass of 75. It had a force of gravity of, let's figure that out. That's going to be equal to mass times gravity, right? 75 times 9.8. That means that our force of gravity of the wagon is 735 newtons. Well, when it was just sitting there at rest, the normal force had to be equal and opposite of it, right? However, when the wagon is accelerating over, that's no longer the case, okay? We have to realize that that net force in the y direction, that's equal to all of the forces acting in the y. And now we have this force applied in the y direction, messing things up, okay? So what is going to happen is that with you pulling upwards on the wagon like that, that is going to result in a decrease in the normal force, okay? So, looking at this delightful thing, if we want to know what the new normal force is going to be, we have to understand that this sum is going to be equal to 0, okay? So, our normal force is going to be equal to our force of gravity, the negative of our normal force, plus our force applied in the y direction, okay? So now, this force over here, the force of gravity is pulling down with 735, so negative 735 plus our force applied in the y direction of 50, which is a positive number. So negative 735 plus 50 gives us negative 686, which cancel out the negative, so our normal force becomes 685 newtons. Okay? Now, let's give you guys a little bit different of an explanation on that. All right? If you're in the grocery store and you're pushing on a shopping cart, okay? This is your cart. You can tell I never took an art class. This is you pushing downwards on the cart, okay? You got this angle here, theta equal to 10 degrees downwards. You are applying a force of 50 newtons. The cart has a mass equal to, let's say, 85 kg. You're buying extra canned goods. Let's see here. I want to know what the acceleration rate is. Also, I want to know what the normal force is acting on you. Okay? So, in normal cases, see what I did there? Normally, your force normal pushes up and is equal and opposite to the force of gravity. Okay? However, here we have this interesting case where we have this force acting on us. Okay, that was weird. And that's going to result in a force applied in the y direction there. So what that means is that your normal force is going to have to counter that. It's going to have to increase in order to actually keep your shopping cart from pushing down through the floor. Okay. You will also have a force applied in the x direction, horizontal. Okay. So what we can do is we can make the assumption that your shopping cart is not going to fall through the floor, and the floor is not going to launch the shopping cart up. So this acceleration here is going to be in the x direction. Another thing that we should note in this problem, for this case, our mu is going to be equal to 0. Okay, that's not exactly true, but we'll go ahead and work with it anyways. Okay, so I want to know my acceleration, and I want to know the new normal force. Okay, so my acceleration, if I want to know that, acceleration equals net force divided by the mass. Right? Now, the net force is obviously going to be in the x direction here, so I should tack that in there. Okay, now let's list out all of the forces acting in the x direction. Okay, so first off, we have our force applied in the x direction. And that's it. Okay, now we have our mass. So what we need to do is figure out what that force applied in the x direction is. So like I've told you before, when you are given a force that is acting across two dimensions, horizontally and vertically, anytime you're given a vector, break it into its components. So your force applied in the x direction in this case is going to be Fa SOHCAHTOA. All right, Fa, this is the angle we're given because it's 10 degrees below the horizon. So that's going to be the adjacent leg, force applied times the cosine of theta. So that means we're going to have 50 times the cosine of 10. I'm going to go ahead and say 50 times cosine of 10 equals 49.24. Okay. Now, I told you to break it into x and y components. Let's go ahead and take care of that. Fay is equal to Fa, and y is the opposite leg, times the sine of theta. So, Fa is 50 times the sine of 10. So, 50 times sine 10 equals 8.68. All right. So now, first question I asked you was for that force or the acceleration in the x direction. We solved over here saying that that was just going to be equal to the net force in the x direction divided by the mass. And so now we can go ahead and plug these numbers in. 49.24 divided by the given mass of 85 kg. And that's going to be equal to 49.24 divided by 85 gives us happiness. No, wait, an acceleration rate of 0.58 meters per second squared. Okay, so that's going to be the acceleration rate you see with your cart as you push it down the aisle. The next thing I'm asking is the normal force. Well, this is a little bit more complicated, but it's still just applying Newton's second law. Okay, we are still going to be using the fact that the net force is going to be proportionate to your mass times the acceleration, right? And our acceleration rate is 0, right? We're not falling through the floor. We're not being launched up off of it. So that means that the net force is equal to 0. So that means the sum of the forces acting in the y direction is equal to 0. So our forces in the y direction We, of course, have a normal force acting upwards. We, of course, have gravity pulling us down. And then we have this force applied in the y direction of you pushing the shopping cart down the aisle. Okay? Now, looking at this bit of fun, we've already solved for the force applied in the y direction. We know that. Okay? Force of gravity, did we solve for that yet? No, we didn't. We were asking for the normal force even. So that's going to be equal to the force of gravity plus the force applied in the y direction. This is one of those cases where we're going to have to kind of take a side trip and figure out the force of gravity is equal to the weight, which is mass times gravity. 85 times 9.8 833. So the force of gravity of just the cart alone is 833 newtons. Okay, now let's do a common sense theorem check. Which direction does gravity pull? Down. Which direction are you pushing? Down. Okay, so now let's put those into here correctly. You have a negative 833 Newton force plus a negative 8.68 Newton force. So 833 negative 833 plus a negative 8.68 equals negative 841.68 newtons equals negative force normal. So in that case, we can cancel out those negatives and we can say the normal force is equal to 841.68 newtons. Obviously, the normal force got a little bit higher here. Okay, if you look at the prior problem, when you were lifting up on it, your normal force dropped. Okay, that's what you should note, or that's what you should experience. If you're pulling up on something, your normal force goes down. If you are pushing down on something, your normal force is going to go up. Okay, this is going to be important because we'll get there in a minute, tomorrow. But you remember that whole force of friction is equal to mu times force normal? Once we are actually dealing with a force of friction, that's going to become a problem. Okay, so we're going to have to incorporate that force into it. Okay, that's where we're going to be going. We're going to make sure that we have these first baby steps down pat with a force of friction equal to 0 first. Okay, so do the practice problems I'm asking you to do. Check your work when I post the keys, and email me if you have any questions. We're going to hopefully be able to wrap this up nicely, before you get back. Either way, take care.